Hello friends, in this video I'm going to show how I designed USB controlled RF switch based around the SKY13453 IC. Let's check the datasheet quickly. The switch operates from 10 MHz to 6 GHz and it requires a single control pin. It selects one RF port out of two based on the V control input. Looking at the table, we get to know that the RF control is when the RF control is logic 1, RF1 port gets selected, and if RF control pin is logic 0, RF2 pin gets selected. Below, evaluation board shows a coplanar waveguide for RF ports. So we'll take this as the reference for designing our board. So let's come back to the schematic since we have finished with the datasheet part. I'll be using the CH32V003 F4U6 microcontroller from WCH Technologies. It's a low cost RISC-V microcontroller, and it can be programmed over a 3-wire serial wire debug port. I will be enabling the USB so that we can control the switch over USB 2.0. Coming back to the RF switch schematics, we can see DC blocking capacitors on all the RF ports. The datasheet suggests that we connect DC blocking capacitors on each RF port, and if you know the internal structure of an RF switch, it makes sense to connect DC blocking capacitors on all the RF ports. Also, we do not want any DC coming in or going out from these RF ports, which can affect the normal operation of the RF switch. Additionally, the datasheet also suggests that the V control pin can accept only a maximum of 3 volts, and for that purpose we have put a voltage divider to scale down the control voltage, which would normally be 3.3 volts level coming from the microcontroller. Unless of course we power the microcontroller with 3 volts, we wouldn't need the voltage divider. So just to summarize what's happening on the screen is I'm taking all the RF connections on the schematic and putting them into one class, into a one net class, and naming that net class as RF, and I will apply special rules to this RF net class, so that whenever I draw a trace or whenever I do a polygon pour, it automatically takes the special rules that I have applied to those. As you can see, it gives me an option to set an impedance profile, which I already set in the layer stack manager. Now whenever I draw a trace, whenever I draw a track for this net, it will automatically take the desired width, track width, to obtain the required 50 ohms impedance. So all the RF nets have been assigned into one net class, and that net class will be drawn with a 50 ohms impedance profile as we set in the layer stack manager. Here I have already done the placement quickly based on the references from the datasheet. Now I am drawing the RF traces first. So whenever we are designing an RF board, always make sure that you give a priority to drawing the RF nets first. Fix your RF nets, fix your RF layout, and then you can focus on the rest of the layout. Always spend more time in perfecting the component placement and then setting up the rules. So when you have a much complex, larger board, the rules which you have already set will automatically take care of the trace width, clearances, and what not. It will basically give you a much easier time while you do the overall PCB layout. As you can see, most of the time I'm spending setting up the rules and constraints, but once I start laying out, it's going to be very quick. Looking closely at the RF switch component placement, we can see the DC blocking capacitors are very close to the RF switch. I've made sure that the RF traces are as straight as possible, going from the switch pin to the capacitor, DC blocking capacitors pin, and then comes the two decoupling capacitors on the right corner. So they came later. DC blocking capacitors came first, then came the decoupling capacitors when I was placing the components. I ensured that I placed the RF traces, the RF components and the input-output connectors first, because you need to have a fixed mechanical geometry in place before you start placing the components, because usually the connectors never move. They are given by your mechanical designer. You place the mechanical components in a fixed position, but you do not usually have control over the mechanical constraints. Now the next major component here is the USB Type-C port, the USB DP and the USB DN. The differential data pair of the USB that needs to be routed next. I've tried to keep it as straight as possible, coming from the type C connector directly onto the microcontroller pins. I have not taken care of any input protection here, but usually you would have a chip that's taking care of the input protection. I've tried to keep it simple. The V bus pair powers up the entire board, so the V bus feeds the voltage regulator, which converts whatever input comes from the USB bus into 3.3 volts output, which is required by the microcontroller and the RF switch for its normal operation. The voltage regulator is a simple one from diodes. It has input and output filtering capacitor, and it gives the regulated output. Now this oscillator connects to the CH32 microcontroller for its clocking needs. This is an SMD crystal with two loading capacitors. The controller, as usual, requires decoupling capacitors on its power pin. Ensure that you are doing all the connections right, since there are not many connections here to do. Everything fits nicely in a two-layer board. Now I come back to the RF section to lay out the ground port required by the Coplanar waveguide. Now since I've already set the rules previously, the clearance between the RF net and the ground is already come in automatically because of the constraints and the rules that are set previously. Using the Altium's net shielding tool, I was able to add uh, ground shielding or shielding vias around the RF nets, as you can see on the screen. The general rule of thumb is that the distance between the two vias in a via shielding should be at least lambda by 8, 1/8 of a wavelength. Considering our largest frequency, the maximum frequency to be 6 gigahertz, our wavelength comes to be around at 50 mm, approximately 50 millimeters. So the lambda by 8 distance comes to around somewhere around 6.5 mm. We are in a very safe margin because the spacing between the two vias here is much smaller than 6 mm, so no need to worry. But the wavelength that we are talking about is in free space. The wavelength on the PCB on an FR4 substrate becomes even smaller, so therefore the smaller spacing between the vias on the shielding makes sense. It should be as small as possible in order to prevent any leakage and to maintain the 50 ohms impedance that we intend to have. I have seen cases where having less number of vias have caused the impedance to not be 50 ohms, to be rather some arbitrary value which deviates from the desired impedance value. So I make sure that I add extra grounding vias near the ground pads of the components, and also sufficient vias around the RF switch. Like I said, I have seen cases where lack of vias have caused the RF circuits to misbehave, especially at higher frequencies. So more vias, just to be safe, just to make sure that we are not short on any vias and we have sufficient number of vias in place for better grounding. And now add a polygon pore cutout to remove the excess copper under the capacitors. Now I do this in order to prevent unintended capacitance being formed in the capacitor. Usually this is known as the parasitic capacitance, and I have no intention of having any parasitic capacitance which could affect the capacitance that is offered by the SMD component. These parasitics make their presence known to the designer by the form of attenuating signals, adding undesired inductance, undesired capacitance here and there in the circuit, which causes the signal to attenuate. It could also cause the signal to radiate. So need to be careful about these parasitics. Finally, beautify your board by placing the silk screen labels correctly, making it easy to read. And here we have our final board ready for manufacturing.